Have you ever looked at, say, a command center or maybe one of those huge video walls at a stadium and just wondered, how on earth do they manage all of those screens at once?
It's a massive engineering challenge.
I mean, we're not just talking about putting one image up there. You're talking about routing what? Maybe 16 different computer signals to 16 different screens.
Exactly. And doing it simultaneously without losing a single pixel of quality. That's the real trick.
And that level of complexity is why you need some pretty specialized hardware, I'm guessing.
It is. So today, we're doing a deep dive into the kind of device that makes it all possible. It's a professional-grade VGA video matrix switch. Our mission here is to understand not just what it does, but why the specs matter so much when the stakes are that high.
Okay, let's unpack that a bit. A matrix switch, that's different from a simple splitter, right?
Oh, completely. A splitter just duplicates a signal. A matrix switch lets you route any input to any output.
So one computer could go to one screen or...
Or that same computer could be broadcast to all 16 screens instantly. It gives you total flexibility.
And the main problem this is trying to solve is what? Signal quality.
Signal quality, absolutely.
Yeah.
And over long distances. Historically, doing this meant signal degradation, or you needed all these bulky interfaces.
You mean those old, clunky, twist-and-lock coax cables that AV pros used to dread?
Exactly. The BNC connectors. This kind of switch gets rid of the need for all that. It just uses standard VGA cables.
Really? Just the simple ones?
Just the simple ones. And every output signal is buffered, which basically guarantees that the image is as crisp and clear as if you were plugged directly into the source.
Okay, but that feels like a trade-off. Usually when you simplify the connection, you lose something, like picture quality or speed. There's no lag or distortion here.
And that's where the high-end specs come in. For these mission-critical rooms, you need something far beyond what consumers use. We're talking about supporting a 1920 by 1200 resolution at a refresh rate of 85 Hz. And that 85 Hz is crucial. It seriously reduces screen flicker.
Which matters for operator eye strain, right? If you're staring at a screen for 12 hours straight.
Precisely. And the bandwidth to push all that data?
It must be huge.
It is. The switch has a video bandwidth of 200 megahertz or even greater, even when it's fully loaded with signals.
And what that means in the real world is that installers can just use copper VGA cables for really long runs, maybe 100 feet or more.
Yes, and without needing expensive signal boosters, it's a huge cost and complexity saver for any large installation.
So that level of reliability, which I see here, is backed by a minimum 24-hour burn-in test for every single unit. That's why we see this tech in command centers, courtrooms, where video evidence has to be perfect, and just massive digital signs that can't afford to fail.
The reliability is just built in. Now, when you think about the routing possibilities, 16 sources to 16 destinations, you need some serious management tools.
Yeah, how do operators actually control all of that? I'm assuming it's not just flipping 16 little switches.
You have a few ways. You can use the buttons on the front panel. There's an LCD screen there. But for real-time control, you're using a serial port or an Ethernet connection. And most importantly, it comes with a graphical user interface.
A GUI.
Right. A control program that lets an operator see the whole matrix on their screen and just, click to make routing changes instantly.
So to sum it all up, the main takeaway is that for any organization that absolutely cannot afford downtime, from a control room to a secure government facility, this is the kind of gear that keeps those visuals running perfectly.
Absolutely. But let me leave you with one final thought to mull over.
Go for it.
The source material mentions you can combine this switch with other components, like a VGA EDID emulator.
An EDID emulator, what does that do?
Well, to put it simply, it provides a perfect digital handshake. It's like a cheat sheet that tells the source computer exactly what kind of display is connected, so it always sends out a perfect signal.
Ah, I see. So there's never any confusion.
Never. So here's the question. If the switch's job is signal distribution, and the emulator's job is to make sure the signal is perfect from the start, how does putting them together change the whole dynamic? What opportunities does that open up for stability and synchronization, especially when you're switching signals rapidly in a critical environment? That's something to think about.